Welcome to this laboratory introduction video about industrial manipulator dynamics. This introductory video will outline and summarize the theory of solid mechanics, structural dynamics, and experimental dynamics which is needed to succeed in the upcoming laboratory. Let's start. Mechanics is the area of physics concerned with the behavior of bodies subjected to forces or displacements. The mechanics branch is further divided into two parts: solid mechanics, which studies the behavior of solid materials, and fluid mechanics, which deals with the properties of fluids in various states and the reaction to forces acting upon them. Solid mechanics is subsequently divided in rigid body, an idealization of the solid body in which the deformation is neglected, and deformable body, that is one that changes its shape or volume when subjected to an external force or changes in temperature. The study of rigid bodies can be further classified into kinematics, statics, and dynamics. Kinematics studies the motion without considering the forces that produce it. When considering the forces or torques, statics deals with the analysis of a stationary system, and dynamics deals with the systems that change with time. A simplified characterization of the industrial manipulator dynamics is the focus of our laboratory. The competitive manufacturing industry is always searching ways to do more efficient operations and to reduce cost. This increment in productivity demands a change on the process parameters. These changes in parameters could increase the cutting or contact forces and put more stress into the structural members of machine tools and robots used for these applications. In machining operations, the elevated thermal and mechanical loads, which could be static or dynamic, may deflect components like slides, machine beds, carriages, spindles, and contribute to form errors that reduce the accuracy of the machinery and the conformance of the workpiece with the expected GD&T. Using modern computing methods and state-of-the-art approaches, it is possible to calculate the static stiffness of a machine and robot components. However, when predicting machine dynamic properties, the damping characteristics of the joints and coupling points are highly uncertain. In industrial practice, it is still necessary to rely on measurements and experimental procedures to judge the dynamic compliance behavior of machine tools and robots, and to select appropriate process parameters which will yield satisfactory manufacturing results. The study of the behavior of structures such as machine tools and industrial robots that are subjected to dynamic loading corresponds to structural dynamics. What structural dynamics seeks to answer goes along the following lines. How does the structure respond to a specific dynamic load? For example, in machining processes, which are the vibration levels at the certain combination of cutting parameters? Which are the conditions when the response is resonant? For example, given these cutting parameters, at what rotational speeds does the resonance occur? Are the resonant responses critical in some respect? For example, if the resonant responses are considerably high so that they originate defects on the workpiece. What measures can be taken to avoid critical responses? Can we increase the damping or the stiffness somehow? Or is it necessary to change the cutting parameters, change the rotational speed or linear feed to avoid exciting resonant frequencies? To facilitate this analysis, we assume that all the systems that we are studying are linear systems, so a linear relationship between the excitation amplitude and the response amplitude is expected. Therefore, they follow these properties. They are scalable. If the input is multiplied by a scalar, also is the output. They can be superposed. The response to several impulses would correspond to the sum of the responses to the individual inputs, and they follow frequency conservation. Therefore, responses cannot contain other frequencies than the excitation. Factors such as friction of the coupling elements will originate nonlinearities in the systems. However, in most cases, linear systems are a very good approximation. These linear systems can be single degree of freedom systems and multiple degree of freedom systems. Single degree of freedom systems are those whose dynamic response can be described by specifying the displacement along only one coordinate. Single degree of freedom systems are an idealization of the mechanical systems. Conventional components of a dynamic system are mass, resulting in inertial force, stiffness resulting in spring force, energy dissipating mechanism resulting in damping force, and external excitation force. In the figures to the left, we can see the response in the frequency domain in terms of amplitude and phase of a single degree of freedom system subjected to a dynamic force with constant frequency. Note the presence of only one mode in the response. In many engineering applications, the real structures are considered multiple degree of freedom systems. Thus, the dynamic problem can be reduced to an algebraic system of equations whose solution is closer to the real one for a dense discretization. As shown in the right figure, M, B, and K correspond to matrices carrying the system information of the mass, damping, and stiffness elements. Usually the masses are lumped and the joints and damping elements are considered massless. In the figures to the left, we can see the response in the frequency domain in terms of amplitude for a multiple degree of freedom system subjected to a dynamic force with constant frequency. Note the presence of two modes in the response for both masses. As mentioned, from the system of equations, an analytical solution can be found to the problem. Unfortunately, finite element methods and other purely theoretical methods are cumbersome to use on complex built-up structures. The main difficulties are to model realistic boundary conditions and the losses of the real structure. Another possibility is to use mathematical models determined from experimentally measured data. The advantage of these methods compared to the pure theoretical methods is that the complex boundary conditions as well as the losses are inherently accounted for in the measured input data. The main problem is that the number of measurements required and the difficulties to obtain reliable measurements. In a nutshell, we could say that model analysis is a process in which, based on measurements, we describe a structure in terms of its natural characteristics, which are the frequency, damping, and mode shapes, so-called dynamic properties. In the classical model analysis, the structure is excited using impact hammers or model exciters, model shakers, whereas in operational model dynamics, natural excitation is used. In both cases, the response is typically measured using accelerometers. Let's consider again the same single degree of freedom system in which we applied a sinusoidal force that has the same amplitude, but the rate of oscillation increases as a function of time. If we measure the response, we will see that it decreases as we sweep up in time. The response amplifies when we apply a force with an oscillation rate that gets closer and closer to the resonant frequency of the system. This time data can be useful, but it is more insightful if we transform it to the frequency domain. Then we obtain something that is called frequency response function, which is the ratio of the output response to an applied input expressed in the frequency domain. Depending on the type of investigation, we need to discretize the structure or to select the points of interest along the structures. In the case of machine tools and robots, these points are generally located close to the TCP where the interaction of the cutting forces and the structure is located. To estimate the FRF, we need to measure both the applied force and the response of the structure simultaneously. The response can be measured as displacement, velocity, or acceleration. Then, the measured time data is transformed from the time domain to the frequency domain using a fast Fourier transform algorithm. Due to this transformation, the functions end up being complex valued numbers that have a magnitude and a phase. From the FRF plot, we can notice that there are peaks. These peaks correspond to the resonance frequencies or the frequencies where we have a maximum response to the input excitation. We have already discussed one of the dynamic properties, which is resonant frequency. We still need to introduce the concepts of damping and mode shape. Damping is the effect that tends to reduce the amplitude of the vibrations by removing energy from the oscillatory system. As we can see in the figure, which is accompanied by the animation, the system response can be underdamped, critically damped, and overdamped, depending on the damping factor. Additionally, the deformation patterns that the structure takes at different resonant frequencies is what we call mode shapes. The animation to the lower right exemplifies the deformation pattern for a beam subjected to a sinusoidal force whose frequency varies in time. Different mode shapes are associated to different resonant frequencies. The understanding of the dynamic properties of the structures will help not only a design engineer but also a process planning engineer to identify how the system will behave when a force derived from a specific set of cutting parameters excites the structure. Once we have estimated the frequency response function, the final step is to use these FRFs to determine the modal parameters. This is accomplished by numerically fitting the theoretical model parameters to the measured frequency response functions by the utilization of different fitting algorithms. During the laboratory, we are going to collect measurement data from the input force, which will be given either by the impact hammer or the shaker, and the output response, which could be either acceleration or velocity collected with a laser scanner, vibrometer, or accelerometers. Then, we are going to use this data to estimate the FRFs, obtain the dynamic properties of the investigated structure, either a machine tool or an industrial robot, and draw conclusions and recommendations based on this information. As a sneak peek, I will leave you with a short demonstration of how this process looks like.
You can now start measuring by hitting the impact hammer onto your system's surface. It will take the setup an average of 3 hits to produce a first set of frequency response functions. Comparing these functions to the occurrence of vibrations during system operation will help you pinpoint the origins of your problem.